I expect the transistor circuit the transistor as a device as well as some of its circuits have already been taught in the class. So I don't want to go into details of how a transistor functions. All we will do here for our purpose is to review its basic principles of functioning and how they will affect the way our circuits are designed and how the circuits will be operated. So here is the basic transistor circuit operated in what is called common emitter mode. This, as you know, is the emitter. This is the base terminal and this is the collector terminal. Other facts that you will recall about the transistor include the fact that in normal operation or what is called active operation, you make sure that this emitter base junction is forward biased. For this kind of a transistor, that means this has a higher voltage than the ground, which is at the emitter's voltage, and further you make the other junction, the base collector junction, reverse biased. This is what we need to do. How we are going to achieve this is a separate question, and there are different ways of doing the same thing. But right now we will understand what happens provided by some invisible means we have ensured that this transistor is operating in the active mode, that is to say that this junction is forward biased and that this junction is reverse biased. So let's see what happens in this particular case. You know something about transistors, bipolar junction transistors such as these, that when it is operated in the active mode, the collector current is a certain multiple of the base current called beta. So IC equals beta times IB, and beta is significantly large. For the transistor that we are going to use in the course, it will be of the order of 100. So if beta is 100, then you will see that since KCL says that IC plus IB must add up to the emitter current, and since IB is such a small fraction of IC, we could approximately write that IC and IE are the same. This is indeed an approximation that we will freely and shamelessly use for all our calculations. Right. So now, given this fact, let us try to understand what voltages will prevail. Between the base and the emitter, we have a forward biased diode junction, PN junction. And we know that when we have a forward biased PN junction, you have approximately 0.7 volts between the base and the emitter, which is at ground voltage. So we can write that VBE equals VB, which is just the notation for the base voltage with respect to the ground, equals 0.7. Now what is the base voltage with respect to the collector's voltage? That's the next question. We know that if this junction has to be kept reverse biased, then the collector's voltage should not be lower, but it should be higher than the base voltage. What we have built up in the circuit here is we have a supply point called VCC, and from the supply to the collector is a certain resistor that we have called RC, the collector resistance. Let's say we have IB equal to 10 microamps. Fine. With an IB of 10 microamps, you would correspondingly get IC equal to 100 times IB of 1 milliamp. Now 1 milliamp flowing through 1 kilo ohm would give you a drop of 1 volt. So the collector voltage is VCC minus 1 volt. So this, for example, would be the result of 10 microamps passing into the base. Clearly, with this choice of a collector voltage, of a collector resistance, and this choice of a base current, you will have this as the point at which the collector will lie, the collector voltage will lie. Now the moment we increase the base current a little more, the collector current will increase proportionately and the collector voltage will come down accordingly. So let's say we make it from, let's make the next calculation at IB equal to 50 microamps. This would give us IC equal to 5 milliamps and VC equals VCC minus ICRC equal to 12 minus 5 equals 7 volts. So this is how the different quantities affect each other. Our first experiment consists of examining the behavior of this network at its extremes. What we will do is to pump in so much base current that the collector current is so large that the voltage of the collector comes down to practically zero. Practically zero is the term because it doesn't exactly come to zero. It comes to a low value called VCE sat, which is the minimum or the saturation voltage that lies between collector and emitter. That's around 0.2 volts. So let's see what base current you need to just enter saturation. In this case, you have 12 volts of the supply to bring down to 0.2. So let's see, VCE sat equals 0.2. If this is the voltage we want the collector to be at, then we want IC RC to be equal to 11.8 volts, which means IC equals 11.8 milliamperes, which means IB equals 118 microamperes. So if you increase IB to as high a value as 118 microamperes, you will end up with saturating the transistor. Anything around, let's say anything greater than 120 microamperes on the base will be too high for the circuit to handle. It will just go into saturation and there will be no more dependence of the collector voltage upon the base current. The other extreme is the cutoff extreme. So this was the saturation extreme. Next is cutoff. When does cutoff occur? Cutoff occurs when the base current is zero. When the base current is zero, the collector current is zero, and so VC goes up to as high as VCC. So IB equals 0, which implies that IC equals 0, which means that VC equals VCC. So what is the range of values over which the collector voltage can move. We can see that 0 is less than not 0, 0.2. VC is set is less than equal to VC, less than equal to VCC. The maximum collector current occurs when the collector enters into saturation, and in this case we know that that is around 11.8 milliamperes, let's say 12 milliamperes for our choice of 1 kilo ohm collector resistor. So IC can vary between 0, which occurs when IB is 0, and 12 milliamperes, and correspondingly the base current varies from 0 to 120 microamperes. So this is the range. Similarly, the lowest value of collector current, which is 0, corresponds to VC equal to VCC, and the highest value of collector current corresponds to VC equals VC sat. Given this fact, we carry out the first experiment, which is just binary operation of the transistor. So what we do in binary operation is to apply extreme values, or take the base current over all extreme values from the lowest to the highest, and see how VC correspondingly varies. The binary circuit essentially makes the transistor alternately go into saturation and into cutoff. We do this by applying this voltage waveform, which is a 5 volt to 0 volt peak to peak at the base through a 47 kilo ohm resistor that's shown over here, and this leads to a similar triangular shaped current, approximately triangular current in the base. The triangular current in the base leads to the triangular current in the collector. Now there are times when the collector current will try to go so high but not succeed because of the limitation of VCC, that the transistor goes into saturation. There are other times at this end where the transistor will be cut off because the collector current goes too low on account of the base current going too low. So both these things will happen. So as a result, in the output waveform, you will not see a triangle, but you will see occasions when the transistor is cut off, when the transistor is saturated. So you would get an output waveform that looks more like this, not drawn to scale with the input waveform, but what you would see is roughly something like this. Here the transistor, this is the collector voltage, the output voltage, and you can see that it cannot go higher than this because this is VCC. So this is the cutoff point. And there are points when the collector voltage will be very low, and this will be the saturation points. The transfer characteristic that you will observe when you apply this triangular waveform through this circuit as the input, and take this as the output and put it in XY mode on the oscilloscope, will be something like this. You can see that this is an inverting characteristic. This is the saturating, this is the time when your output voltage is very high, corresponds to the cutoff region. This region from here to here corresponds to the active region, and this part corresponds to the saturation region. So this is one simple demonstration of how a transistor can be made to invert a waveform. This is doing an approximate inversion of this. When this goes high, this goes low. When this goes low, this goes high.
So today we will see the demonstration of experiment number 6 of ESC201 Lab. The experiment is on the bipolar junction transistor. So we are here using a BC547 transistor. The first part of the experiment is the BJT inverter circuit. So here is the BC547 transistor. The pin diagram is given in the handout given to you. You first place these flat circles towards you, and starting from the left side, the first one is the collector terminal, the second is the base one, and the third is the emitter one. So we have already wired the BJT inverter circuit as per the setup shown in the figure 2 of the handout given to you. So we have the function generator. To adjust the function generator to obtain a 200 Hz triangular wave. So the triangular wave is shown in the channel 1 of this DSO. So as you can see, this triangular wave varies from minus 2.5 volt to plus 2.4 volt. It is almost 5 volt peak to peak. So we have to adjust this waveform from 0 to 5 volt. For that you have to adjust the offset knob of the function generator. As I adjust the offset knob, this waveform is shifting from almost 0 volt to 5 volt, and here we obtain the 0. We have to obtain the output of the BJT inverter circuit from the collector terminal. So this collector terminal is being connected to the channel 2 of function generator. Once we press the channel 2 knob, this output is being shown. So as you can see from the waveform, this output is somewhat an inverted form of what the input is being given. So to obtain the output, we have to connect the channel 2 probe to the collector terminal. So this is being connected to the channel 2. As you can see, in the channel 2 you can see a wave which is almost an inverted form of what is the input being given. So this one is so we have to observe the transfer characteristics of the BJT. For that, we have to go to the XY mode. And here is the transfer characteristics of BJT inverter circuit. Yes.
So this is the amplifier circuit. The amplifier is supposed to act as a linear system and convert the input to an amplified or magnified version of itself. As you already know, it is inherent for the BJT common emitter circuit to have an inverting property. When the base voltage goes up, the collector voltage goes down, and vice versa. So while this will do an amplification, what it will produce will be some inverted amplification. That is to say, if you have Vi of t as the input, then Vo of t will be equal to minus k times Vi of t, where k is the amplification factor and k will be greater than 1 by some amount. So this is the kind of behavior one is supposed to expect from a transistor amplifier. Now let's get into the details. This is a more sophisticated circuit. It takes care of various other things that we have glossed over until this point of time. The first thing is proper active operation. I have already said that in order for the transistor to operate in the active region, the emitter base junction should be forward biased and the collector emitter base junction should be reverse biased. The way to do this in this particular example is this. we have VCC supplied both to the transistor itself, as is passing through here, as well as to a potential divider. The potential divider values have been adjusted so that the right amount of voltage goes to the base. Since current is flowing in this direction in both these resistors, and since the base current is so small compared to the current through this divider, the divider resistances are kept sufficiently low to ensure that the base current that takes off from this side may be neglected. Obviously no current, DC current can go this way because of the capacitor over here. So we could essentially assume that this behaves as an unloaded potential divider. The lower part of the voltage is now the base ground voltage, not really the base emitter voltage, because there is also a resistance here whose purpose is a little too complicated to explain. It's called RE, and its purpose is to stabilize the behavior of the transistor under temperature variation. We will not worry about RE right now. The fact, however, is that RE will drop some of the varying collector voltage, which should have actually occurred across the collector resistor over itself as well, and therefore cause a significant loss of amplification. But there is a workaround for it that we will discuss in the last moments of this presentation. As of now, the point to be made is that you have a certain base voltage, base ground voltage sufficient under normal operating conditions to keep this base emitter junction forward biased. You have a reasonably larger base collector voltage, rather supply and base voltage, to keep the collector voltage reverse biased. Collector reverse biased. Now the one important thing should be understood. We already have considered in the previous part of the discussion that there is an operating range for the collector voltage, an operating range for the collector current, and so on. So if you want to have a proper amplifier, and if you believe that the input voltage will be symmetrically distributed about 0, then the output voltage will also be symmetrically distributed about 0. The output voltage, even under the largest input voltage swing, should never really touch VCC. It should be slightly below that to prevent its getting distorted. For the same reason, the output voltage should never really go too close to VCE sat, because that again would lead to distortion. Keeping these facts in mind, it becomes clear that for the kind of design we had kept in mind earlier, where VCC was 12 volts, right, and IC operated from 0 to 12 milliamps, we should choose a collector current that is exactly half as the operating point of the transistor when no input is applied. This should be the collector current. When 0 input is applied from the input source, there should be a collector current, a quiescent current of 6 milliamps. So we want IC 0, or this is not required by our standard notation. IC must be kept at 6 milliamps, and when it is 6 milliamps, these through our 1 kilo ohm resistor, actually the handout will tell you what other values of collector resistor to use, etc., than the ones I am describing here. The purpose of this presentation is to make the calculations simple. You will be using, actually, according to the handout, a 3.3 kilo ohm collector resistor. You have to make your calculations accordingly. But for the 1 kilo ohm resistor that we had in mind, these are the appropriate calculations. So for a 1 kilo ohm resistor, you have IC must be equal to 6 milliamps under quiescent conditions, and then VC will be equal to 6 volts. So it can swing downwards to 0 by up to 6 volts and upwards to VCC by an amount of 6 volts. So VC is right in the middle. So one should attempt to achieve this by a proper adjustment of R1 and R2. Indeed, it might be convenient if you used a potentiometer in one of these or in series with one of these to fine tune the operating conditions to exactly these values. Now once this is done, the transistor is ready to be used as an amplifier. Now let's see what things are left to be done and what things are left to be discussed. These bias currents and voltages are DC quantities. We don't want them either to enter the load, to get loaded and therefore get modified by the amount of loading that occurs, or we don't want them also to get into the input source. So the countermeasure for that is to put capacitors that block DC signals both on the input side and on the output side. So all the DC magic that occurs in this circuit occurs strictly between these two capacitors. VCC comes in here, the DC current, some of it flows in here, some of it flows in here, and here, and then it goes out to the ground here. There is no lateral or horizontal movement of the DC currents out on this side or on this side. These DC currents, DC voltages are only to prepare and position the transistor at the right point on the operating curve. Now having done that, we will apply a purely AC signal over here, sinusoid, triangular wave, whatever you wish to amplify. What we are going to use according to the handout is a 1 kHz sinusoid. You apply that over here and the AC flows in because the capacitors will not block the AC signal. It goes in here. Some of it gets loaded by these resistors, but that's alright because this is pretty much an ideal source with a very low output resistance. And the AC current adds to the DC current and enters the base. So what now enters the base is a mixture of AC and DC. What therefore appears at the collector is also a current that is a mixture of AC and DC. What, however, causes the ultimate variation of the collector voltage as a function of time will then again consist of a DC component and an AC component. The DC component stays right here, the AC component manages to be seen through the capacitor at the output point. So that is how this system works. And at all times, we want to make sure that the peak-to-peak amplitude of the input sinusoid or varying waveform remains within the active region. Make sure that the circuit remains within the active operating region of the transistor so that you get faithful though inverted amplification at the output without distortion. So much for the amplifier's behavior. More details are available in the handout. There are a few last comments to make. As I said, there is a certain loss of amplification due to the presence of RE. But for reasons that are a little complicated to explain, the presence of RE does improve the behavior of the transistor circuit. Now let's see. What happens if this loss of amplification has to be controlled, has to be reduced, has to be remedied? What we do is to put a large capacitor across the emitter resistor like this. This capacitor will allow the AC signal to completely ignore the presence of RE because this capacitor will act as a much lower impedance pathway for the AC signal, though it will completely block the DC signal. This will give us the best of both worlds. It will give us excellent amplification, as good as if RE were not present. At the same time, give us stable behavior of the transistor circuit, which would happen only if RE is present. So this is the final refined circuit model for the common emitter transistor amplifier. One thing does happen that you have to take care of. The placing of this large capacitor, which is almost as large as 100 of microfarads or maybe 50 microfarads or something of that sort, will cause the amplification sometimes to go so high that even with extremely small values of Vi of t, you will get too large an output swing and cause distortion of the output. The only way to correct this is to make this extremely low. And since normal signal generators, function generators that you will use have limitations on how low you can turn the knob, what we do instead is to make a slight modification. We place the function generator over here and use a potential divider to drop, let's say, 90% of the function generator's voltage and pass on only a small amount of that voltage into the rest of the circuit. This, of course, might be considered a waste, but it doesn't matter. Really, what we want is a sufficiently weak signal of only a few millivolts peak to peak to enter the circuit. And all this is required only when the amplification really goes up on account of placing an emitter capacitor over here. What is called a bypass capacitor. Emitter bypass. To bypass the AC signal while not affecting the pathways of the DC signal. So more details, tabulation, calculations, etc. are given in the handout, and this is all we need to cover in this presentation.
The second part of the experiment is the common emitter amplifier. We will wire the circuit with only the resistors RC, R1, R2 and RN. Now we have to measure the node voltages VB, VC and VP. So we will bias the transistor using a 12 volt supply and we will measure the collector voltage. So first we will measure the collector voltage. And as you can see from the multimeter, the collector voltage is coming to be around 3 volt. Now we will measure the base voltage, and as you can see it is coming to be around 3.4 volt. Now we have to ensure that the transistor is in active mode. So we have to measure the voltage across the base and emitter junction. So as you can see, the base emitter voltage is coming to be around 0.64 volt. So the transistor is acting in active. So after measuring the node voltages VP, VC and VE, you are supposed to estimate the currents IB, IC and IE. Then you have to compare between the theoretical and the measured results you got. So after that we will switch off the power supply and we will again come back to the circuit. We will now connect the coupling capacitors and the load resistor. Then we will adjust the function generator to obtain a sine wave of frequency 1 kHz and amplitude 200 millivolt. Now we will connect the function generator output to the base of the transistor via a coupling capacitor. So here is the input waveform. It is 200 millivolt, the amplitude is 200 millivolt and the frequency is 1 kHz. Now we have to obtain the output from the collector terminal via a coupling capacitor. Here as you see, to the channel 1 we are given the input, and from the channel 2 you can obtain the output. So as you see from the SO window, the output is an amplified as well as inverted version of our input. So CE amplifier is basically an inverting amplifier. So as you can see, it is inverting the input and it is an amplified version. Now we can measure the amplification. So from here you can see that the Vmax is almost 600 millivolt to the given an input 200 millivolt. So thus we can obtain the amplification factor of the CE amplifier. Next we will change the value of the resistor RC from 3.3K to 15K, and now we observe the change in the output. So in the channel 2 we will observe the change in the output. From here you can see that the volts per division is 50 millivolt, and here you can see the distorted output. And now you have to verify whether this amplifier provides any gain or not. Now with RC equal to 15 kilo ohm, you change the amplitude of the input signal and see the differences in the output. So to the last part, we will change back our RC from 15 kilo ohm to 3.3 kilo ohm, and we will connect a capacitor of 100 microfarad across the resistance Re. So here we go a 100 microfarad capacitor, and we will observe what is the change in the output. As you can see from the DSO, the output gets saturated. See, this is channel 2 is set to 5 volt per division, and the output is almost 10 volt peak to peak. So this indicates that the gain of the amplifier circuit is too large for the circuit to hold, and we have to decrease the input signal amplitude either using the function generator, or better to use a potential divider circuit as given in the handout. So that is left.